Good afternoon, everyone. Hope all is well. Hope everyone's doing all right. Let's see, it is 12:33. So it look like this is who we have. Let's see if everybody's logged in. Okay, cool. So as I said, hope everybody's doing great. Hope everyone's doing all right. Last class, we started 6.3, law of large numbers. And we are now here at expected value. All right. So I think all audio are connected. Okay. So expected value of a variable is the weighted average of all its possible values. And because it is an average, the expected value is likely to be close to the actual value only when there is a large number of events. So that the law of large numbers come into play. And we see right here how to calculate expected value. It says consider two events, each with its own value and probability. Expected value based on these two events will be the value of event one times the probability of event one, plus the value of event two times the probability of event two. And so this formula can be extended to any number of events, including more terms in the same format or same flow. So however many events you have, you would just continue on with this pattern, multiplying the value times the probability, and then just add it to what we have here. So I'll give you a chance to write that down, and then we'll go into the first example. All right, scrolling up some. Looking at that first example, suppose that $1 lottery tickets have the following probabilities and values. So 1 in 5 to win a free ticket, which is worth $1. 1 in 100 to win $5. 1 in 100,000 to win $1,000, and 1 in 10 million to win $1 million. What is the expected value of the lottery ticket? And so we'll discuss the implications and come to a conclusion. But I'll give you a chance to write that down for those who are writing. All right, so let's look at how we would calculate these events. Created a chart. You don't always have to create a chart, but this is just a way to keep everything in line. So notice the first row is a ticket purchase. So the dollar value is negative because you pay out $1, and the probability is 1, which represents 100%. So if you're going to go throughout this process of buying a lottery ticket, you have to pay $1, and it's a 100% chance that you're going to lose that $1, right? That's why it's negative, and that's why this probability is 1. So that's the first part of our probability, -1 times 1, which is -$1. All right. So then the second event is a 1 in 5 chance to win another lottery ticket, which is worth $1. So that's where this comes from. $1 times 1/5, which give you 0.2, which is 20 cents. The third probability or third event is that 1 in 100 will win $5. So we do 5 times 1 over 100, which is just 5 cents. And then the next moment, we're looking at 1 in 100,000 can win $1,000. Multiply those together, you get 1 cent. And then 1 in 10 million could win $1 million. Multiply those together, you get 10 cents. So now adding all of those together will give you a negative 64 cents. All right, so before we look at our conclusion and what this means, questions on what we did here, how we calculated anything, where these numbers came from in reference to our problem. Any questions? And of course, I'll give you a chance to copy this down, but just any questions while we are copying? It is right from the book. Let me find the page. I know it's 2 something. Look, 208, page 208. No problem. So the expected value is going to be the sum of all the products times the probability. That's what we did here. And it ended up being negative 64 cents. So in other words, on average, you would lose 64 cents. If it was positive, that means you would gain it. But since this ended up being negative, that means you actually lose 64 cents for each lottery ticket that you buy. So if you notice this last statement right here, if you buy 1,000 tickets, then you would expect to lose 1,000 times 64, which is $640. On average, you would expect to lose that 64 cents. So you would expect to lose like $640 if you purchase 1,000 tickets. Questions on what we did here before we look at another one? Can I scroll up? All right, the next one, you are at an art auction trying to decide whether to bid $50,000 for a particular painting. You believe that you have 50% chance or 50% probability of reselling the painting to a client in New York at $7,000. Then you believe you also have a 25% chance or probability of reselling the painting to a client in San Francisco for $80,000. Otherwise, you would have to keep the painting, which has its own benefits, but not monetary ones. What is the expected value of the $50,000 bid? I'll give you a chance to write that down for those who are writing, and then we will evaluate. right, so we're gonna look at the 3 moments or 3 events that we have to consider. So the first one is just like when you go back to that lottery ticket, there was a 100% chance of spending about $1 when it comes to the lottery ticket. So here, there's a 100% chance of spending $50,000. So there's probability of 1, which represents 100% that you're going to pay $50,000 for the painting. That's the only way you can go ahead throughout this probability of selling it for 70,000 or selling it for 80,000. So then there's a probability of 50% or half to sell the painting for 70,000. Then probability of 1/4 to sell the painting for 80,000. And so this is how it looks when we start our calculation. Once we're paying out the 50, so that 50,000 is negative times 1, but we're gaining 70. If we sell the painting, we're gaining 70,000. So that's why that's positive times the 1/2. And then the same thing with the 80,000. That's why that's positive, because we're selling it. We're going to gain 80,000. There's a 25% chance that we would gain the 80,000. So it's a negative 50,000 plus 35,000 plus 20,000, which will ultimately give us a positive $5,000 gain. So I'll give you a chance to write these things down for those who are writing before we scroll up. All right. So conclusion. So with the $50,000 bid, on average, you could expect to gain $5,000 by the purchase. But it's important to remember that the expected value refers to the expected gain or loss over many purchases. So you should not expect to earn $5,000 in a single case. So it's possible that in a single case, you could earn more, you could, but on average, if you were to continue this process, you would expect to earn on average $5,000. Questions? Any questions? Make sure we're okay. All right, any questions? Can I scroll up? Everybody okay? All right. One of the last things that they talk about in this section is the gambler's fallacy. So it's the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or that a streak of good luck will continue. So when it comes to probability, especially when things are equally likely to occur, as another thing, to think that something is about to happen because it hasn't happened yet is actually a mistake. It's an erroneous thought that it does not have to happen. It does not ever have to happen because of the probability and how things are equally likely to occur. All right, next thing, streaks, which feeds into the gambler's fallacy thought process. So there's a misconception when it comes to streaks. Suppose you toss a coin 6 times and the outcome is heads, 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 heads. In other words, all heads. Then you toss it 6 more times and the outcome is heads, tails, tails, heads, tails, heads. Most people would say that the second outcome is more natural, while the first outcome is surprising. So, but in fact, both outcomes are equally likely. All right, yep, that's it for 6-3. Questions, anything before we go to 6-4? 6-4 is relatively light as well. Got more calculation than 6.5. Next class, we'll do 6.5. And that will close out chapter 6. And I'm thinking we should be able to get it done within one class period. But 6.5 has more calculations in it. And they calculate probabilities, independent, dependent events, and so on. So everybody done with the purple? Yep. So 6.4 deals with ideas of risk and life expectancy. Life expectancy is the number of additional years a person of a given age can expect to live on average. Yes, yep, that's fine. Not a problem at all. All right, scrolling up. So does a 50-year-old person have the same life expectancy as a 20-year-old person? So a 50-year-old person will have a shorter life expectancy than a 20-year-old person because a 50-year-old is not expected to live as many additional years as a 20-year-old. So it is exactly how it sounds when you talk about life expectancy and what is expected from a 50-year-old versus a 20-year-old. All right, scrolling up. Okay. I'll go too far, let me know. So next thing, risk and travel. Travel risk is often expressed in terms of an accident rate or death rate. Did I hold on to read? All right, suppose an accident rate is 750 accidents per 100,000 people. This means that within a group of 100,000 people, on average, 750 will have an accident over the period of a year. All right, scrolling up. So another example for the 11-year period of 2002 to 2012, the total number of deaths in commercial airplane accidents for the United States was 158 for an average of about 11 deaths per year. By the end of this period, the total number of miles flown by commercial aircraft was about 8 billion per year. So use these numbers to calculate death rate per mile of air travel, then compare the risk of flying to the risk of driving. So that's based on a chart that was given. That's that's just comparing the values. The main thing is how do we calculate it, and that's what I want to emphasize with this example. So I'll give you a chance to write for those who are writing, and then we'll look at calculating. All right, so we're going to look at what we want to calculate, what they want us to calculate, I should say. So it says use these numbers to calculate death rate per mile of air travel. So don't forget, per is always going to be your division sign or your fractional bar. So what comes before that will be in your numerator, will come first, and then what comes after that is going to be in your denominator. In other words, come last as far as your calculation is concerned. So we're looking at the death rate per mile of travel, air travel. So we have 11 deaths per year. So that's 158 on average, and on average, so about 11 deaths per year. Then by the end of this period, the total number of miles flown is going to be 8 billion per year. So that's how they have this calculation right here, 11 deaths per 8 billion miles. And so we have 0.0000000014 death per mile. All right, question before we go any further. If it was mile per death, then it would be flipped. Not sure that makes much sense, but I'm just using that as an example. If it was mile per death, then it would be 8 billion over 11. And then you calculate that out. So what comes before per is going to be on top. And then what comes after per would be what's on bottom. And you would divide it in that way. So This risk is about 1.4 deaths per billion miles. So when you get in the math lab, more than likely what they're going to do is either, well, they're probably going to give you a couple statements to choose from. And so if it says here, like it says, the risk is about 1.4 deaths per mile, per billion miles, excuse me. What you would do is take 1 billion, multiply it times this number, and you should get 1.4. Same thing here, or 0.14 death per 100 million miles. If you take 100 million and multiply times this number right here, you'll get 0.14. And so that's how that works. So let's say if they said 14 deaths per billion. But when you take a billion, you multiply times this number, you get 1.4, then you know that answer is not the right one because it's saying 14 instead of 1.4. So that's how that works. Just take this number right here and multiply to the number that you calculated, or here 100 million, and do the same. And then you see that they compared it to 1.1 death per 100 million miles for driving, but that was from the previous example. So all they would do is comparing the two numbers. But my main thing here was to emphasize how do you get this number, and this is how you do so. Questions. Let's see, that the last one. Yeah, that's the last one out of 6 points. All right. So as you can see, we do have time. We could jump into 6.5, but once again, I try to give you guys a chance to process this information that I gave you. I gave you 2 sections here. Next class, we're going to do 6.5, which is only going to be 1 section. But that's our last section to close out chapter 6. And after that, we'll actually be looking at posting a test for you guys for chapter 5 and 6. So that you'll be able to move forward. Let me see how far does this go as far as our sections are concerned. Don't keep me out. So let's see, we got 7, 8, 9, 10. Okay, it's not too bad. So we'll close out 6.5 and then we'll look to get into 7. Okay, not bad. All right, so I know I had one question. Somebody had a question out of chapter section 5.3. Did anybody else have anything before I go into that specific question? Did anybody have any general questions before we go there? So everybody good? What we done? Questions on the lecture? All right. So what I'm about to do is answer questions. If you don't want to stay back for questions, you don't have to. Next class, like I said, we're going to get into 6.5 and go from there. So if you guys are good, I'm good. Some questions aren't going to come up till you actually get into the assignments and start doing work. So once you do that, feel free to ask questions away. Other than that, you guys have a good one, be safe, and stay back if you have any questions. So Ms. White, so you had a question about something in 5.3?
Yeah, I was just looking. I forgot exactly which question. I ain't doing it in a minute. I gave up. Let me see. 1 second. I know it was on math lab. I couldn't get question 4 Lord Jesus, 5.3 right at all, and I did it twice and I just didn't understand.
You know what was number 4?
Number 4. Yeah, that one right there.
Right here? Okay. Let me see what you got going on here. Assume that the weights of adult female normally distribute the mean is 79, standard deviation of 20. All right. Take this picture. What's me? Okay, let me go back, try to take a picture again. All right, so assume the weights of adult females normally distributed with the mean. Our mean is 79 degrees. I said that's 79 degrees, 79 kilograms. Standard deviation 20 kilograms. What percentage of individual females weights less than? We're talking about less than 82 kilograms. I guess I can put the numbers here. That's the first question. I guess I'll call it A. And then B is the samples of 36 adults, males are randomly selected. So that means N is 36. What is the mean weight computed each sample? What percent of the means is less than? And I believe we call it X bar. Here. Okay, this book don't call it X bar anyway, so I'll take that off. All right. So let's look at the first one. It says what percentage of, first of all, they gave us the mean, gave us standard deviation. And it says what percentage of individual adult females have weights less than 82 kilograms. All right, so that is just a regular Z-score formula problem. Where you just take your data value minus the mean divided by standard deviation. So even if you don't like the symbols, you got your data value minus the mean divided by standard deviation. So that's the formula. So your data value is always the value in question. So you're talking about being less than 82. And then our mean was 79. And their standard deviation was 20. And if you have any questions, feel free to stop me or, ask me to slow down, whatever. So that's 80 minus 79 divided by 20. And that gives us 0.15. So our Z-score is 0.15. Any problems so far?
No.
And always remember, we're looking for 2 decimal places. This ended up being 2 decimal places anyway. But if it went further than that, you want to round it to 2 decimal places. So now we're going to go to the Z-score chart. I'm trying to pull it up. Oh, I should have it already. Wait one second. Yeah, I do. All right, so here's the Z-score chart. So we're looking for points 1 to 5. So 0.1 is right here, and 5 is up here, and where they meet is the chart value that we pull. So that's 0.5596. So before I go back to the notes, any questions on how we did the Z-score chart?
No.
All right. So chart value, I'm just gonna call it CV. Chart value is 0.5596. Now the chart value, let's say chart always here less than. So if you're looking for less than, then you just use the chart value. If you want it greater than, you subtract the chart value from one weight. We talked about that back in, I think it was 5.2. Trying to see if this, where did I put that summary? There you go. Summary right here. So anything that's talking about less than, you use the chart value as the answer. Greater than, you're going to subtract the chart value from 1. And then if we're talking about between, that means we need 2 z-scores. You would subtract both chart values from each other. So those are your 3 scenarios. So we're talking about less than, so we're going to use the chart value that they gave us. So 5596 should be, or 0.5596 should be the answer. Let me go here. All right. So now they asked us to round to 1 decimal place as needed. Get out of here. Stop. Okay. So the answer is the 0.5596, but they gave a box with percentage on the outside. So that means they want to convert this number to a percent. So you move your decimal 2 places to the right. That's 55.96%. But then they ask for 1 decimal place. And so that means that that 6, since it's 5, since it's greater than 5, or greater than 4, I should say, it's going to round that 9 up. So that's 56.0. And that's your answer. So before we go to B, or the second question, is that okay? Make sure we're all right.
Yeah, thank
Yep, no problem, no problem. Anybody else before I go to the next part of her question? Okay, we got somebody else in here. Everybody good? Oh, only one other person. Okay, that's fine. If you have any questions, feel free to ask. So now looking at B. Okay, so B says if the samples of 36 adult females are randomly selected, and the mean is computed for each sample, what percentage of sample means are less than 82? So when it comes to our mean, we're going to still use the same mean, which was 79. And then when it comes to our new standard deviation, let me see what symbolism this one used. I know different books use different symbols. No, where did it go? Oh, they didn't write one. They didn't use a symbol. Okay, that's why I didn't know. All right, so our new standard deviation got to be standard deviation divided by the square root of n. So our standard deviation was 20 divided by the square root of 36. And I believe that's what we had. Yep, 36 is n. So this is 3.3 repeated. And our data value is still 82. So the z-score will be 82 minus 79 divided by 3.3. You can write down as many threes as possible, because the more you write down, the more you use the calculation, the more accurate your answer is going to be. So I would say go about 5 or 6 behind the decimal. All right, and it ends up being 0.9. Go out and decimal places. Make sure I got this right. So 3 divided by 1/3. 9, that's 0.9. Yep. Okay. So z-score is 0.9, or in other words, 0.90 if you round it to 2 decimal places. Now we need to go to the chart, get that chart value. So we're looking at 0.90. 0.8159, so it'll be 0.8159. And then once again, we're looking at less than. So this is the answer that we need. All right, so and I believe this goes to percentage as well. I'm about to check in a second, which would be 81.6%. Yep, and that's what they needed.
Thank you.
No problem, no problem. Is that all you needed?
Probably not, but that's good for now.
All right, I'll wait till next time. All right. So if you guys are good, I am good. Y'all have a good one, be safe, and I will see you on Wednesday.